So I sent you an email with extra credit possibilities. So there are 3, each for 5 points. So one on pH and titratable acidity, one on fat characterization, and one on protein separation characterization. They're all posted in their respective weeks on Canvas, and a handful of you really need them. So please consider doing the extra credit, Riley, on Canvas. I was talking about the extra credit opportunity. Each one of you, please consider doing them. It could be a failing to a passing. It could be B plus to an A minus. So these are learning targets, and it helps you learn as well as help you get points you need. So consider doing that. We said pad characterization due Monday, pH and titratable acidity due next Wednesday, and then next Friday protein characterization will be due. Okay. Okay. Let's recap and continue from where we left off on Monday. I know you had the pH and titratable acidity in the middle, but let's continue. Hopefully try to remember where we left off. So where do we utilize protein separation? Can you remember? You can look back at your notes. Axel? Purification for what purpose? Future analysis. Yes. Purify protein and characterize it, understand its functionality, understand its chemistry, or probably use it for enzyme use. Ali, where you had your hand up?
Yeah,
Production of protein ingredients. Nathan?
Well, the purified protein, like to study it more, I guess, for like research.
Yeah, that's what we were just.
Yeah.
Yeah, you're confirming what Axel said. Okay, thank you for confirming that.
Of course.
One more, if you're looking at effect of processing on what happens to your protein in the system, because the protein impacts color, impacts flavor, impacts texture in your final product. So you can characterize what happens to the protein upon processing by just extracting it, isolating it, looking at its structure and how it's impacting functionality. What are some methods for separation and isolation of protein? Yes, Megan? Ion exchange chromatography, which is a subset of adsorption chromatography. So ion exchange could be cation, anion. What else? Size exclusion chromatography, which we have not talked about, but yes, you had that size exclusion in your mind from last time, didn't you? I love your hat. What is that?
Found in my grandparents' basement. It's in New Orleans, Party Town.
Oh, party group? Oh, cool. Separation by differential solubility. That's the big thing. Salting out with salt, pH, isoelectric focusing, denaturation by solvent or by temperature. So differentiating solubility is really a big thing in isolation of proteins. Okay, we will continue with the methods. We have other methods. We talked about HIC last time as well, but there are other methods that we will continue with. Since we talked about ion exchange and we know chromatography very well now, so this is a question that's actually one of the questions on your practice sheet that is posted on Canvas. Let's try to think about it together. Take a moment, read the question. When you think you have a reasonable answer for the first part, raise your hand. Just think about it though. Take a moment, think about it. Thank you. Thank you. So what's the ask here? We have a mixture of proteins. The one that you're interested in has a PI of 4.5. The others in the mixture has a PI between 6 and 6.5. PI means isoelectric point. That means the pH at which you have zero charge. So you want to get that protein that has that specific isoelectric point using ion exchange chromatography. In order to determine whether you want to use anion or cation exchange, you first have to think about what charge do you think you want your protein of interest to be at. So you want to think about your buffer and what charge you want that protein to carry versus the other proteins in the mixture. Then you can decide whether it's going to be anion or cation. Do you know the charge of a protein above its isoelectric point? Would it be negatively charged or positively charged? Oh, guys, you should know this from your food chemistry. You don't?
You said above.
Above isoelectric point.
Negatively charged?
Negatively charged. So above the isoelectric point, your protein mostly is negatively charged. Below the isoelectric point, it gets protonated, so it becomes mostly positively charged. All right. So what happens if I pick a pH of 5.5? What would be the charge of those other proteins I don't care for versus the charge of the protein that I care for if I pick a pH of 5.5? Yeah?
So the ones at the 6 range would be positively charged and the 4.5 would be negatively charged?
Okay. And since I have a mixture of several of those that can be positively charged, and I really need the one that is negatively charged, and I pick the 5.5, do I use anion or cation exchange? Remember, anion is exchanging anions with your stationary phase. That means negatively charged. So what do I pick? What's easier? You can pick either, but what's easier for you? The easier is anion exchange. Why? Because then in your, the positively charged will not interact with the column. They will just go with your void volume. They will not interact, and then your protein of interest will latch on to your stationary phase. So it will be held back. Everything else will just move forward and elute in the wash. In the wash, that means in the void volume. It's the same kind of term, different two terms for the same thing. Okay, so we kind of answered all of these parts. How will you elute the protein that binds to the column? So now your protein of interest bound to the column, how will you let it come out in a decent amount of time, not just wait and wait? It will eventually diffuse out of the column, but what would you do to the buffer, to your mobile phase? Remember that you increase the strength of the mobile phase to speed up or to elute your component of interest. How can I increase the strength of the mobile phase? In this case, yes, Riley? Increase the pH of the buffer, yes, because if I increase the pH of the buffer, the positively charged groups on the column will lose a proton. They will become negatively charged. They will no longer attract my negatively charged protein. It will just come off. Okay? So if I increase the pH, I have more of OH minuses now in my buffer. They will strip off protons from the stationary phase. Then my stationary phase will no longer be positively charged. Okay. Another way you can increase salt. So salt will displace your protein on the column and will help the protein move down the column. Okay, so If I ask for one way, you can pick one or the other. If I ask for two possible ways, that would be increasing salt concentration and increasing pH over time. All right, good. So next, we're still talking about adsorption chromatography. Another form of it is affinity chromatography, where we are looking for specific interactions of our protein of interest with the column. So it could be our ligands on the stationary phase could be antibodies. That's very specific for certain protein of interest. It could be enzyme inhibitors if we are isolating enzymes. It could be lectins for any glycoproteins if we're isolating glycoproteins. So basically that's a refresher from chromatography, but with an application for protein separation and isolation. And what you do is, once it is bound and everything else goes out with the wash, the way to get it out is you change the ionic strength or the pH of the buffer, because the interactions are very specific. Once you change the ion and you change the pH, then you are changing the charges on that protein, then it will not interact as well with with the functional group on the stationary phase. Or you can, if you're doing general protein separation with lectins, then you will add lectins to the buffer, then the protein will be displaced by interacting with the same group, but that one that is free in the buffer. Okay. Moving on to separation by size. So far we talked about differential solubility, we talked about adsorptivity, and now we're going to move on to talk about separation of proteins by size. So in this example here, I'm showing the dialysis tubing. Some of you might seen dialysis tubing before. Some of you might not have not seen it before. It's just water, so I'm putting my hand in there. So basically it's a tube with pores. The pores can be of different sizes. So this one in particular, because I know we have that in our lab, is a 3.5 kilodalton cutoff. So anything less than 3.5 kilodalton cutoff, if I put it in water, by diffusion, high concentration to low concentration, then you will, anything lower than 3.5 will move towards the water. So what happens is at some point you get equilibrium. Right? What's inside is equal concentration-wise to the outside. Then you change the water, and you keep it there for a few hours, and then another equilibrium is reached. Okay? You keep doing that until the concentration of everything less than 3.5 kilodalton is very, very small concentration. You'll never have zero, because it's always an equilibrium between inside and outside. So why do we use this? You can look at it and pass it around. It's nothing dangerous in there. What we have is a blue dextrin, just to show color, different color. So why we use dialysis most often is to remove salt or small sugars. If we isolated our protein in a mechanism that has salt in it, like salting out, or using hydrophobic interaction chromatography, then we want to remove the excess salt. The best way to do that is via dialysis. So that is the most common application for dialysis for proteins, is removal of salts or small sugars from your sample. There is also diffusion, there is osmosis, so there's water that can go in as well inside of the tube, and the tube can bulge and become really a lot of water in there, and then you dilute your sample quite a bit. To avoid that, often we have a polyethylene glycol layer on the membrane, and that prevents water migrating inside and making it too dilute. So it's good for concentrating the sample. Okay. So next, using membrane filtration. So there is small scale membrane and there large scale membrane. So for example, I'm going to be passing a tube here. Inside the tube, there is a membrane. So you put your sample on one side of the where the membrane is, and then this can be centrifuged. So by centrifugal force, you can force anything with water, with anything less than the cutoff of the pore size, because the membrane also has pore sizes. So for example, this one has 30 kilodalton cutoff. So often you want to separate proteins that are larger than certain molecular weight and get rid of anything smaller, or vice versa. Sometimes you want to get rid of everything large and contain only the small. So if I'm looking at peptides and I want to characterize the bioactivity of peptides, then I want to get rid of anything greater than 10 kilodalton, for example. I just want all the peptides that are less than 10 kilodalton. So I don't care for the retentate, I want the permeate. Permeate is what comes through your membrane. Retentate is what stays on the membrane. So it's a very unique tool. They come in different sizes, small, even a smaller 1 milliliter size as well, depending on the size of the sample. And they can be very, very large industrial size. So whey protein isolate, for example, lots of companies produce it by membrane filtration, basically. And the pore size of the membrane determines whether it is a microfiltration, an ultrafiltration, nanofiltration, or reverse osmosis. So with different types of membranes with different pore size, reverse osmosis, nanofiltration, ultrafiltration, microfiltration, you are, the retentate and the permeate will be different based on size. So the permeate for reverse osmosis will be very small, 100 Dalton will pass through, and anything greater than 100 Dalton will not pass through. And similarly for nanofiltration, there's a range between 100 and 1,000, and so on for ultrafiltration. And microfiltration is really large molecules get to be retained. So here's an illustration of the different membranes at what can you retain and what can be permeable. So if we take milk, what's in milk? Yeah, of course, we have bacteria in milk, fat, protein, lactose, minerals, and water. I want to separate the different components. If I put microfiltration there, I'm retaining the bacteria and the fat and protein, lactose, minerals, and water pass through. If I have another membrane with ultrafiltration size, then I'm retaining everything greater than 10,000 Daltons, which mainly are the proteins. So I'm retaining the proteins, lactose, minerals, water will go through. If I want to retain everything except my minerals, keep the lactose, for example, nanofiltration. Lactose will be retained, minerals will go out. If I want to purify my water from minerals, I have the reverse osmosis. And we do that quite a bit for research purposes. So we do have a reverse osmosis setup in our lab to produce mineral-free water for research. It's always good to work with mineral-free water. Call it deionized water. Yes?
It's kind of an off-topic question, but
It's
how
fine.
these membranes are produced? These pore sizes so small.
Oh dear, I don't know how they're produced. Some people in engineering figured that out to produce them. Sorry, you can ask Ray. I'll send you to Ray. He might know. Okay. Chromatography, separation by size. So we do that a lot in the lab on a research scale, and it's also done in industrial scale. So you can separate proteins based on their size. So you can get all those small, if you generate hydrolysate and you care for bioactive peptides to put them in pharmaceutical type of application, then you want to separate those small ones from the large proteins, then you can do size exclusion chromatography to do that. And please review chromatography for the final. It will be in everything. And just a refresher in size exclusion, those big ones will go out with the wash if they're bigger than the pore sizes. The smaller they are, they will go within the pores of the particles that you have in your column and will be delayed. So larger proteins will elute first, smaller proteins and peptides will elute last. Size exclusion chromatography can also be called gel filtration or gel permeation. The three of them mean the same thing, separation based on size. They call it gel here because you are actually forming a gel kind of type of your media. When you mix your media with water or buffer, you kind of form sort of a gel. Electrophoresis is one of my favorite tools in the lab, and I've done a lot of electrophoresis in my early years as a graduate student and as a postdoc. This is actually me as a postdoc. These pictures were taken from me a few years ago. But anyway, so have you seen a gel before? Have you worked with electrophoresis? Raise your, yeah, my graduate student very excitedly raised their hand. Okay, those of you that, oh, look, we have a bunch of you guys. Where did you do gel electrophoresis?
We do it in general biology.
Ah, cool. I didn't know that they do them in general biology. I didn't when I took general biology. Okay, but a refresher. Don't get too excited. Okay, so I'm going to show you what the gel looks like. I'm so excited. I haven't done that for a while. At least I do it once a year in food analysis. Okay. So nowadays, the gel come pre-made for you. You have a cassette, we call this a cassette, and it's basically 2 layers of plastic in this case. Between the 2 layers, there's a thin layer of gel that has been formed with acrylamide. Okay, so acrylamide, and there is a cross-linking agent that we put in there to solidify the acrylamide. And depending on the concentration of the acrylamide, the higher the concentration, the smaller are the pore sizes. Okay? So with higher concentration of acrylamide, you tend to separate proteins of smaller molecular weight. Often in this case, it is a gradient gel. That means you have different concentration of acrylamide across the gel. So you can separate proteins that are from a range of sizes, very small to very large. Because then you have a range of pore sizes, not all the same pore size. They change because you're changing the concentration from bottom to top. Okay, so we do have a comb in here. So, and before you use the gel, you want to pull that out. And that allows the current to go through because you're going to run a voltage, apply a voltage, and a current will be run. And then you put your gel. Back in the olden days, when I was a student, we didn't have these. We had to make our own cassettes from glass. It took a whole day to just prepare the gel and the next day to run the gel. So you just put it inside of the criterion cell, and you put a running buffer. So a buffer there that will allow current to go through. We call it running buffer. And then once you have the buffer, you remove the comb, and then you have little wells that are separated by little pieces of gel. So you can use a pipette, a very small pipette with a very thin tip, very unique tip, not the same tips that you use in the lab, unique tip with a very thin end that you can insert, and you usually pipette depending on the well size, anywhere between 5 to 30 microliters of your sample. And then you close this and apply current, apply voltage, and then your protein will move down your gel. Now, we have three different types of gel. You have the STS-PAGE, sodium didecyl sulfate. You add that to your sample. It makes all your proteins carry negative charge. So now your proteins, all of them have the same charge, so they only separate based on size. So they go down the gel and separate based on their molecular weight, with the smaller ones going down faster, following the current. Once the current is generated, negatively charged proteins are going to go towards the positive charge. So they're all going to go down, but the smaller ones will go down faster. So if you look here, there's a molecular weight marker. So this is 7 kilodalton, the smallest, and 195, the biggest. And then these are protein mixes. So they separate based where they are. And the presence of markers allow us to determine where the subunits of these proteins are and how big they are relatively. It's a qualitative method. Okay, so you ran your gel. Usually your sample is run with a dye so that you get to see that the blue mark going down the gel. That's when you know that your samples are going down because proteins are not colored, so you just put a dye in there. Once your all of your sample ran all the way to the bottom, then you take it out and then you break it. We have a cool compartment here where it's made just to break your, that's the favorite part. Broke it. And then you gently open it. Now this is an old gel. It might crack, but usually we use a wash bottle of water to ease the gel out without breaking it. It's a really thin layer of gel made of acrylamide. I'm not wearing gloves. Is it because I'm old and I don't care? Or why do you think I'm touching the acrylamide with my hand and not caring, other than I'm old and don't care? It's a polymer. It's polymerized. Acrylamide will not hurt you if it's a gel form. So do you want to touch it? Are you going to trust me? Yeah, she trusts me. Okay, so yeah, you can pass it. Whoever wants to touch the gel can touch the gel. So you take the gel. Usually we don't play with the gel. We try to ease it into a container. And we use a dye that will bind to your Kumasi blue, that will bind to your protein. And then we destain it so that it's not all gel is blue. What remains blue, only the proteins. And this is how we see them. Because the Kumasi blue binds to the protein, then we can visualize. We take a picture, we visualize it, we can see our proteins. You broke the gel? It's in multiple pieces. By the time it reaches Isabella back in, there's no gel. I'm sorry. It won't get to you. Okay. Allie, don't feel, you look so disgusted. It's just polyacrylamide. Okay. We can do cool things. Oh, hold on. I just want to mention that there is UreaPAGE. UreaPAGE is basically you put urea reagent with your sample, and it will denature the protein, but it will not make it carry charge. So the protein also will separate using a polyacrylamide gel, but your sample is not all negatively charged. So in this case, your separation is based on charge to size ratio. Because some proteins are very similar in molecular weight, but they differ in charge, so you really want to separate them on the gel. You'll see that in chemical reactions when you separate casein, for example, you won't be able to separate them very well with STS-PAGE. They will all come clumped together. But when you use UreaPAGE, you can separate beta casein from alpha S1, alpha S2, and kappa casein. So you can separate them because these proteins differ in charge. Native PAGE is you separate the protein as is. You do not put any denaturing agent or any agent that will cause negative charge. So you will separate them as is. It doesn't always give you a separation because some proteins are similar in charge, in molecular weight. So really when you separate them as is, you might not see a lot of differences. That's why it's not really common. Most common is SCS PAGE. Next is UreaPAGE for these unique proteins that are different in charge but similar in size. Okay, we can do isoelectric focusing. Isoelectric focusing meaning we're separating the proteins based on the isoelectric point. So in this case, we get a strip, another little piece of gel, a strip, and what we do, we create a gradient. We create a pH gradient on that strip. How do we do that? Is we apply at one end ampholytes, a mixture of ampholytes. That means these are small polymers that carry both positive and negative charges. And then we apply the voltage, and then they will start separating and moving. The positives move toward the negative, and negative goes towards the positive when we apply the gel, then when we apply, the voltage, and then you formulate a gradient of different pHs on your strip. Then you load your protein in one end solution, and then you run a current. Then the proteins will migrate, keep moving until they hit their isoelectric point. Once they hit their isoelectric point, they will precipitate out and they will move no longer. And then thus we separated them based on their isoelectric point. They can then, if we want to do further testing, they can be removed, excised, for further examination. The cool thing you can do, okay, there's another gel here. Chelsea gave it to me because it's expired, so I can open these gels and not worry about losing money. Research money is valuable. Okay, but this is expired. This one, if you can see, it doesn't have wells. It has one whole big well. What is this for? It is for 2D gel electrophoresis. So here in the place of that one big comb that doesn't have any wells, you take it out, and the strip that you used for separating based on isoelectric point, you can insert it here. So you will have a strip. The strip can go in here, and then you run it. You make sure that you have your strip put in STS, so all the proteins in your strip now are negatively charged. And this way, when you run it, they go down and separate based on size. So first dimension, we separated them based on charge and isoelectric point. Then the next dimension is separating them based on their charge. If anybody wants to play with a gel, I can break that. Or later. Okay, so what you see here from this example, what's the power of 2D electrophoresis is because proteins there's so many proteins in the world, and they're so complex, and some of them are really similar in isoelectric point, others are really similar in molecular weight, and if we really want to separate them and identify their functionalities and characteristics, for example, their allergenicity, determine if one compound is more allergic than another, I really want to separate them as much as I can. So if you see here the blue one, for example, the blue band, in that region we got 2 proteins. This means this band was not pure. We had 2 different proteins at different molecular weight because one is larger than the other. Here they separated really well based on their isoelectric point. When we ran them down the gel, they are still 2 separate ones, but similar molecular weight. So that is emphasizing why 2D electrophoresis is sometimes really helpful, because you can differentiate based not only on size or not only on isoelectric point, but on both. That adds to the power of separation. You can use electrophoresis for more quantitative analyses, which is capillary electrophoresis. It's a unit that gives you quantitative data. How so? It has a similar principle of separation with electrophoresis, but you can take your samples that get separated and pass them through a detector, similar to an HPLC detector. It seems like it's similar as if you have a chromatography with a column, but instead of a chromatography, it is electrophoresis. So then samples get separated, and after they get separated, they go to the detector and you measure them. Detectors can range from UV detection to light scattering detector or pulse detector. So any detector that we've talked about that works for HPLC will work for capillary electrophoresis. So it's called capillary because you really have a very narrow tube that contains either fused silica with silanol groups without any gels inside. Here the separation is based on pull of charges. So silanol groups are negatively charged, so any positive ions from the buffer will bind to the negatively charged, and once a current is generated, the positive charges will go towards the cathode, and they pull with them different protein molecules and separate them based on their charge. So first the positively charged, then the negatively charged, then the neutral proteins. That's the order. Positive, negative, neutral. In that capillary, you can have a gel that is regular acrylamide gel, and you can separate based on size. Or you can have an alpha-lights, and you can separate based on isoelectric points. So this is a form of quantitative separation and then quantitative detection. Okay. Let's take a moment and look at this question. I have a mixture of proteins. I want to separate them. One, X has a 90 kilodalton molecular weight and plus 5 net charge. Y has a 30 kilodalton molecular weight and plus 5 net charge. So I have similar charges here, different molecular weight. And Z, I have similar molecular weight to X, 89 kilodalton, yet a different net charge. Which of the following I can use to separate those three proteins? Anyone? Huh? C and B. Okay. Anyone else? Devin, A and C. One more? Riley, is that you or Daniel? Your voice sounded like two people. It's all of the above. It doesn't matter what order. You can start with cation exchange and then do size exclusion. With cation exchange, you're separating the first one from the other two, and then you separate the other two by size exclusion. It doesn't matter. Or you can separate X and Z from Y by using size exclusion, and then you can separate X and Z by cation exchange. So it doesn't matter the order. B, you can also use salt to precipitate the protein with +2 charge first, and then you end up with those that are with a more charge that remain in the solution. And these you can separate using a membrane separation with a cutoff of, say, 35 kilodalton. So everything less than 35 will go through, and then that would be your permeate, and then the retentate will be the 90 kilodalton protein. So you can do any of those and get to similar result. Now you separated the protein, and sometimes you want to look at its characteristic. The first thing you want to consider is the protein quality. Because when you report protein content on the nutrition label, sometimes some labels you'll see percent daily value. The percent daily value, you don't only get it because of the quantity. If you have 25 grams of protein, how much proteins you need a day, do you know? Do you remember that value from your nutrition course? 50 grams a day. So if you have 25 grams of protein, it doesn't automatically state that you have 50% daily value. 25 over 50 is 50%. It's not like that. You have to take into account the protein digestibility and the protein essential amino acids. In order to do that, you have to determine a certain number. We call it PDCAS, protein digestibility corrected amino acid score, and use that score to multiply by the quantity of the protein. Well, I'll have it on a slide later on. But first, we look at amino acid composition, because this will tell me the different essential versus non-essential amino acid. And it will tell me the first limiting amino acid, which is the amino acid that is essential and present in the least quantity. And then digestibility. How digestible is the protein? Plant proteins are less digestible than animal proteins, for example. It has to do with their structure. Processing can reduce digestibility of the protein or increase it, depending on the processing condition. Anti-nutritional factors. I have enzyme inhibitors like trypsin inhibitor, for example? Or do I have lectins that cause inflammation in the intestine? So the protein analysis is done by, first of all, the amino acid composition is done by breaking all of the peptide bonds. In order to break all the peptide bonds and release all of the singular amino acid, typically you hydrolyze with a strong acid for an extended period of time until all peptide bonds are broken, and then amino acids are separated either by ion exchange or reverse phase chromatography, and we use standards to quantitate. In order to quantitate, we cannot directly measure UV because not all amino acids absorb UV light. Only 3 of them do. So phenylalanine, tryptophan, and tyrosine. So in order to be able to detect all of them, we have to react with a reagent, either ninhydrin, and measure absorption at 570, or phenylthiocarbamyl or ophthaldehyde. We can measure absorption at 340, or fluorescence with ophthaldehyde. Then you can determine the composition of amino acid in your protein, and from there you use it in your PDCAS, protein digestibility corrected amino acid score. So you get the milligrams of the first limiting amino acid in your test protein and get the ratio of it compared to reference protein. Reference protein almost always is casein, is used as a reference protein. So you want to do digestibility. So we get the amino acid score, and I want the digestibility score as well. This is done using rats. So you feed rats a certain amount of protein, and then you measure nitrogen in their feces. Then you would determine the amount of nitrogen absorbed versus the amount of nitrogen intake. That gives you the true digestibility. Then you have the digestibility score, and you have the amino acid score. Then you get the PDCAS, which is the value out of 1. So 1 is the highest PDCAS, and anything less than 1 is less, it has less quality, basically. And for nutrition label, the percent daily value, so how many grams of proteins you have per serving, you multiply it by PDCAS, and then you divide it by the amount of protein needed per day. So if the PDCAS is 1, that means great, 25 grams of casein in your serving is available. All of it is available, then that gives you 50% daily value. If it's 0.8, that means it's not all available. So that is how we determine PDCAS. I'm going to go quickly over protein efficiency ratio, 1 minute. It is done only on infants, for infant food, that is. It's not done on infants, it's done on rats, baby rats. And basically what they do is they feed the baby rats a certain amount of protein, and then they determine their growth. How much did they grow? And then they correct that with a reference. And usually a reference is the casein. So this PER is not done for adults because we really hope that not with every gram of protein we consume we keep growing. So that doesn't apply to us. The rate of growth of infants is equivalent to the rate of growth of baby rats. So that's why it works for infants. So protein efficiency ratio and PDCAS for everything else other than infant food. Okay, I can stop here. We have a couple of slides, but I'll finish them on Monday.